Hello everyone, today we're going to knock out 2.5, which is called implicit differentiation. It is a new differentiation technique that will help us handle unusual situations that might pop up from time to time in our equations. Now, everything we've done up to this point, it's always been an explicit equation, y equals f of x equals f of t equals s of t equals. The y value of the equation has always been isolated to allow us to take the derivative with respect to x, and then our answer was simply either y prime or dy dx or f prime of x. But oftentimes there are relations or equations that are very difficult to solve for that variable in question. Now that we have the chain rule, though, we have something called implicit differentiation, and we're no longer restricted to that need to get y by itself. For example, y equals 1 over x is an explicit formula because it's solved for y. But if x was multiplied to the other side, another version of this equation would be x times y equals 1, and regardless of which way it's presented, the derivative should be the same. But how do we take the derivative from this form, x times y equals 1? We don't need it in this case because we can solve for y easily, but what if the equation was something like x squared minus 2y cubed plus 4y equals 2? Getting y by itself there would be very difficult, and then we would have to take the derivative of whatever was left over. So hopefully we can find a technique for finding the derivative if y isn't isolated. And to do that, we have to understand how the derivatives have been taking place so far, usually with respect to x or t or something on the other side. And that means when you took the derivative of x alone, you would just get 1. But in the case of taking the derivative of just y, we'll have to apply the chain rule because, the derivative of y may be 1, but it's times the derivative of y with respect to x, very similarly to the way that the chain rule we would work outside in when doing the derivative. Okay, so the three examples down at the bottom illustrate how this kind of works. When we take the derivative with respect to x of x cubed, we just operate normally. We bring the 3 down, we lose 1 from the power, and the power rule is 3x squared. But if you do this with y cubed, you still do the same thing. 3 comes down times y squared, but it's times dy dx because there's an extra factor of taking the derivative of y with respect to x, whatever y is. Similarly, our other rules apply. If you took the derivative of x plus 3y with respect to x, the derivative of x with respect to x is 1, but the derivative of 3y with respect to x is 3 dy dx. So this kind of illustrates some of the situations we'll arrive in for taking the derivative. It also illustrates that we don't actually need to solve for y. As long as we recognize how the chain rule applies here, we can take the derivative implicitly. So here's our general guidelines for implicit differentiation. You'll differentiate both sides of the equation with respect to x, but each time you take a derivative that has y in it, you'll need a dy dx in there as well. And then to solve for your derivative of y with respect to x, you'll collect all of your terms with dy dx to one side and everything else to the other side, and then you'll factor out the dy dx and divide whatever remains. And we'll see when we take second derivatives and things like that, we have to sometimes be clever with our substitutions. So let's start with find dy dx using implicit differentiation. We have y cubed plus y squared minus 5y minus x squared equals negative 4. This one would be very hard to solve for y. So when we take the derivative, we're doing it with respect to x. So as a reminder, I'm going to write d dx to represent we are taking the derivative with respect to x. So y cubed becomes 3y squared, but times dy dx. Y squared, the power comes down, 2y times dy dx. The derivative of negative 5y is just negative 5 times 1 times dy dx. The derivative of x squared we know to be 2x. Since the derivative is with respect to x, there is no dx dx. And on the other side, the derivative of the constant would be 0. Anything with a dy dx we want to keep on one side, but I need to take this 2x and move it to the other side. So we will continue to write all of the other terms, but we will add the 2x to the other side. So this is all equal to 2x. Because now everything on the left has a dy dx, you can factor it out. Dy dx times 3y squared plus 2y minus 5 equals 2x. And now we have dy dx times something, but I want the derivative by itself, which means I have to take whatever it's multiplied by and divide it to the other side, which means dy dx equals 2x divided by 3y squared plus 2y minus 5. Because we're doing this implicitly, sometimes my answer will have both x's and y's in it. That's totally fine. That's not a problem at all. So let's try this again with one more. This one's relatively basic, but I wanted to illustrate that there are ones where you're going to be forced to use this. In B, you could potentially solve for y, but it still illustrates that implicit differentiation could be faster. So when we take the derivative with respect to x, this is 2x plus 2y times dy dx equals 0. Again, I need to have whatever with a dy dx on its own side, so we will subtract the 2x. So that 2y dy dx equals negative 2x. And again, there's something times dy dx. There's nothing to factor out here, but I can divide by the 2y on each side to get that dy dx is equal to, the 2's will cancel, so it'll be negative x over y. And this can even come into play with some of our other rules as well. xy squared equals 3x. Sometimes this is the product of two things. We might have to use product rule. So if we use product rule here, it's x times the derivative of y squared, which would be 2y dy dx, plus y squared times the derivative of x, which is 1, is equal to the derivative of 3x on the right side with respect to x, which is 3. So this is 2xy dy dx plus y squared equals 3. I want to solve for dy dx, so I'll subtract the y squared to the other side. So we get 2xy dy dx equals 3 minus y squared. And then finally, again, this is all multiplied together, so we have to divide to get it by itself. So that dy dx is equal to 3 minus y squared over 2xy. So this is a mechanism. It's really just an application of chain rule, but it's going to be incredibly useful moving forward in certain word problems. And we'll see in the next video what exactly we can do with this applied to, say, finding slopes of tangent lines, finding slopes of graphs at certain points, because in the past, solving for y, we were kind of restricted to functions or relatively easy things to work with, and now we can work with basically anything. And like I said, we'll see in the next video.